Good morning, I'm Gawidan, and I'll be presenting to you today a run-through on hexapod robots that are closer to being indestructible. First of all, what are hexapod robots? Hexapod robots are mechanical vehicles that walk on 6 legs. A robot can be statically stable on 2 or 3 legs, but a hexapod robot provides a greater potential for flexibility in terms of movements due to the degrees of freedom the additional legs can provide. Indestructible here refers to the capability of the robot to figure out how to continue its motion as a response to various damages it may encounter. In movies which have giant robots trying to kill you, chopping off a leg or two will never be enough, as they will find a way to carry on and kill you. This is the start of that kind of technology. So, how is this achieved? The T-resilience algorithm applying a transferability approach was used to do this. The purpose of the transferability approach is to cross the reality gap that separates behaviors optimized in simulation to those observed on the target robot. The main proposition is that the algorithm is made aware of the limits of the simulation, then a regression algorithm, a statistical process for estimating the relationship between variables, is used to compare the ideal working state of the robot to whatever current state it's in. What happens is that the damaged robot embeds a simulation of itself, and behaviors that rely on damaged parts will not be transferable. In other words, they perform differently in simulation and reality. The parts of the robot are classified as not working as expected and working as expected, and this kicks off the adaptation process. A transferability of function then maps descriptors of solutions to a transferability score that represents how well the simulation matches reality. Optimization via Pareto dominance is then done. Pareto dominance searches for the most optimal trade-off by having to satisfy two conditions. First, that the solution P' is not worse than P with respect to all objectives, and second, that solution P' is better than P with respect to at least one objective. This process is repeated until a satisfactory compensatory gate is obtained. The initial process needed an average of 20 minutes for the robots to determine a satisfactory compensatory motion, and in the case of small robots, 20 minutes of life is a very big issue. Recent developments, however, have allowed the adaptation period to be reduced to an average of 2 minutes. This has been done by eliminating most of the experimental discovery involved in the previous process. Instead, the robot runs through a bunch of pre-discovered gates via a 6-dimensional behavioral repertoire, evaluates a series of them, and then selects the best. This repertoire is quite extensive, containing approximately 13,000 different gates. It took 2 weeks to create using a robot model running in simulation, and around 20 million iterations of a gate generation algorithm. But since you only ever have to do it one single time for each robot, and it can be done at design time before deployment, it saves you time in the field, which is where the time is actually important. Shown in this slide is an example of a behavioral repertoire of a hexapod robot missing a leg. This repertoire stores high-performing behaviors at each point in a 6-dimensional behavior space. Each dimension is the portion of time that each leg is in contact with the ground. The behavioral space is discretized at 5 values for each dimension. Each colored pixel represents the highest performing behavior discovered during repertoire creation at that point in the behavior space. The matrices visualize the behavioral space in 2 dimensions according to the legend in the top left area of the picture. The left matrix is one of the 8 pre-adaptation repertoires. During adaptation, the repertoire is updated as tests are conducted, in this case, in the damaged condition where the robot is missing one leg. The right matrix shows the state of the repertoire after a compensatory behavior was discovered. The white circles represent the order in which behaviors were tested on the physical robot. The red circle is the final discovered compensatory behavior. Amongst other areas, high-performing behaviors can be found in the first 2 columns of the 3rd dimension. These columns represent behaviors that least use the central left leg, which is the leg that is missing in this case. Here we can see an actual visual representation of the hexapod robot in the field. The pictures on the upper half show the trials during the first stage of the development, while those on the bottom show the application involving the behavioral repertoire. Important to note here is the discrepancy seen between the trajectory the robot takes once the damage occurs and the improvement as it tries different behaviors and eventually arrives at an acceptable compensatory behavior. The application of such technology is seemingly limitless, as it is applicable to almost the entirety of robotics. The capability of a robot continuing its function despite certain setbacks increases its overall reliability and efficiency in doing work for man. What has been presented so far encapsulates the adaptation and problem-solving process to continue functioning, but all those functions aren't set in stone. That is totally up to the rest of society, and this is where the greater possibility of innovation comes in. Having searched extensively on the authors of these papers and on the algorithms developed, no directly related patents were found for this. I have therefore just included the abstracts of the published papers on these developments on this slide. A lot of developments in this particular field are bound to arise given its relevance, and maybe then patents will